Hi everybody, welcome to your third AP Statistics video. This video is going to teach you all about z-scores, which are a huge topic in AP Stats. And in fact, z-scores are going to come up from here all the way through to the end of the year. So it's important that you learn these really well. So the reason for z-scores is sometimes we care more about the relative standing of data points than we do the actual values of those points. In other words, I might not care so much about my actual test score. I might care more about where my score falls in relation to everybody else. In these cases, it's useful to be able to calculate a z-score. What a z-score measures is the number of standard deviations away from the mean. So an observation z-score would be how many standard deviations away from the mean it is. Z-scores have both magnitude and direction, meaning the size of the z-score tells me how far away from the mean I am, and the positive or negative sign in front of the z-score tells me if I'm above or below the mean. So if my test score has a z-score of positive 2, that would mean that my test score is 2 standard deviations above the average test score. Z-scores are actually very simple to calculate, assuming that we know the mean and standard deviation of the sample that I'm pulling from. In order to calculate the z-score, you take x, which is the actual observation that you're trying to find the z-score of, you subtract the mean, and you divide by the standard deviation. That's all. So x minus the mean tells me how far away it is, and then dividing by the standard deviation puts that in terms of standard deviations. For example, if I score a 68% on my first AP Stats test, and let's say the mean and standard deviation on that test were 70 and 8 respectively, meaning the mean score was 70 and the standard deviation is 8, then the question is, what is my z-score? I'm going to start with the formula. Z is equal to x minus the mean divided by the standard deviation. X is my score, which is a 68, minus the average score is a 70, divided by the standard deviation is 8. And if I subtract and divide that, I get negative 0.25. The negative tells me that I'm below the mean, and that makes sense. I got a 68 and the mean was 70. And 0.25 means I'm 0.25 standard deviations away. So this z-score, this negative 0.25, means I am 0.25 standard deviations below the mean score. Let's do another example. This says Eleanor scores 680 on the SAT math section. The distribution of SAT math scores is single-peaked and symmetric with a mean of 500 and a standard deviation of 100. Notice they just gave me center, shape, and spread. Shape, single-peaked and symmetric, that sounds approximately normal. Center, the mean is 500. And spread, the standard deviation is 100. Okay. Gerald takes the ACT and gets a 27 on the mathematics portion. ACT scores also follow a symmetric single-peak distribution, but with a mean of 18 and a standard deviation of 6. We want to find the standardized scores, in other words the z-scores, for both students, and then assuming both tests measure the same kind of ability, we want to know who did better. So I'll start down here with Eleanor. Again, z is equal to x minus the mean divided by the standard deviation. Eleanor's score was a 680, minus, for the SAT, the mean score is 500, divided by the standard deviation is 100. So when I do that, I get a z-score of 1.8. And just to clarify, this means that Eleanor's SAT score was 1.8 standard deviations above the average SAT math score. Now we can do this for Gerald as well. Again, I start with the formula. Z is equal to x minus the mean divided by the standard deviation. Gerald's ACT score is a 27 minus the average ACT score is 18 divided by the standard deviation is 6. When I do that, I get a z-score of 1.5. So Gerald's ACT score was 1.5 standard deviations above the average ACT score. Z-scores allow us to compare apples and oranges. Just looking at it, I can't tell if Eleanor's 680 is higher than or lower than Gerald's 27. I can't directly compare those two. But z-scores allow me to do that. I can see that Eleanor's z-score of 1.8 is higher than Gerald's z-score of 1.5. So assuming that both tests measure the same kind of ability, it does appear that Eleanor did better. We're going to do one more example to practice calculating z-scores. So this example says 3 landmarks of baseball achievement are Ty Cobb's batting average of 420, which happened in 1911, Ted Williams' 406 in 1941, and George Brett's 390 in 1980. These cannot be compared directly because the distribution of batting averages has changed over the years. So we can't compare a player from 1911 to a player from 1980 directly. Instead, we're going to use z-scores. So the distributions are all quite symmetric except for outliers like these 3 players. Compare the standardized averages for Cobb, Williams, and Brett to compare how far each stood above his peers. And like I said, we're going to do this with z-scores. So let's go ahead and start with Ty Cobb. We know that z is equal to x minus the mean divided by the standard deviation. And Ty Cobb's batting average was 0.420 minus, he played in 1911, so I'm going to use this row right here in order to see what his z-score was as compared to other players from his decade. So the mean in his decade was 0.266 divided by the standard deviation in his decade was 0.0371. I'm obviously recording this at home because you can hear my cat in the background. So let's go ahead and subtract and divide. And I get a z-score of 4.15, which means that Ty Cobb's batting average was 4.15 standard deviations above or better than other baseball players during his decade. Now, I want you to pause the video and calculate the z-scores for Ted Williams and for George Brett. So please pause the video right now, and I want you to calculate those 2 z-scores. Okay, let's check your work. Here is the z-score for Ted Williams. So it's x minus the mean divided by the standard deviation. Ted Williams' batting average was 0.406 minus the mean for his decade. He played in the 1940s. So the average batting average, I know that sounds weird, was 0.267 divided by the standard deviation of 0.0326, which gives me a z-score of 4.26. So Ted Williams was 4.26 standard deviations above other baseball players during his decade. And finally, for George Brett, his z-score is going to be his batting average, which was 0.390, minus the average for his decade was 0.261, divided by the standard deviation, 0.0317. And that gives me a z-score for Brett of 4.07. So even though we're told in the problem that we can't directly compare these three players' batting averages, we can compare their z-scores because these are standardized values. And so by looking at these, we can see that all three of these were very good baseball players. They had wonderful batting averages. All of them were more than 4 standard deviations above the average batting average of their decade. But we can see the one that stands out the most is this 4.26 for Ted Williams. So if we compare just batting averages, we would see that he stands out the most when compared to the peers in his decade. So that's all I want to say about z-scores, but I do want to bring up one last thing, and that is percentiles. We actually already know another measure of relative standing, and that is the percentile. We've talked about this several times in class, but I want to remind you, a certain percentile is just a value with that percentage of observations below it. So if I tell you that your height is in the 25th percentile, that means you are the same as or taller than 25% of people. And we know that the median is the 50th percentile. Quartile 1 is the 25th percentile. Quartile 3 is the 75th percentile. And just to make sure you remember this, let's say Jenny got an 86 on her test, and 22 of the 25 scores in her class are less than or equal to 86. To find her percentile rank, we're going to take the number of people who scored at or below Jenny's score and divide by the total number of people in class, and we see that that's 88%. So Jenny scored at the 88th percentile on this test. That's it for relative standing. Please answer the questions that follow this video and come to class tomorrow prepared with some questions. Thanks, guys.